wonder, should I leave the music on real low or is that distracting? I kind of like it on really low, but I don't know. But also, if you can't hear me, that would be bad also. All right, let's get started. Yeah, having a second monitor would be very useful for sure. All right, let me get rid of this text. Okay. Should be all set to go. Yeah, so actually, yeah, maybe it might be distracting me a little bit actually. Yeah, probably better without the music. Right. So at the end of last time, I think Mavwort had the, obvious question: how do we prove that the main statement that we were basically talking about the whole last time? So, yeah, in order to do that, I'm going to introduce a few concepts first. So we're going to talk about a moment generating function for a random variable, and then we'll talk about the central limit theorem, which, very fundamental, foundational. I guess you could probably say it's like the fundamental theorem of probability, even though I've never heard it called that. But this is the theorem that says, if we take a bunch of random variables that are all identically distributed and they all have, some finite mean and variance, and we take some sum of them, and we have to do some like rescaling, which we'll see in a bit. But if we do everything carefully, then what we get in the end is this perfectly symmetric, standard normal variable, basically, if we rescale everything, etc. Yeah, I really liked your stream today, Mavwort, as well. That was quite nice. So yeah, we have a moment generating function. So let me just define that for you first, because we haven't really talked about this at all. And there's also this Levy continuity theorem, which I'm going to kind of be using. I'm not going to prove it. I don't think I could probably prove it off the top of my head. I'd have to look it up, but I don't think it's too hard to believe if you've dealt with these functions before. Yeah, this is like a common proof technique in probability, so that's another reason to go over this. So moment generating function. Yeah, gonna need some new markers soon, but let's see. Okay, I think we can read this, right? Maybe I'll switch to blue. The blue one seems to be really, really good. So moment generating function, this is going to be a function of one variable. I think maybe if there's multiple variables, you can have, or multiple random, like a joint random variable, you could have it in multiple variables, but let's just keep it simple for now. So we have a random variable x, and we're going to say that the moment generating function is a function of t. It's the expected value of, and then I take e to the power of, and I take our little variable t times the random variable. So x itself is random, so e to the power of t times x, t is just some number, right? We just plug some number in here. So this is also some number, e to the t x is some random variable, and we're just saying what's the expected value, and this is just some sum, basically, or it would be an integral if your random variable was over a like infinite probability space. But right here, I think we're just, for now, we'll just be dealing with finite stuff. So yeah. And why is this called the moment generating function? Basically, it generates the moments in some sense. Well, it doesn't generate them, but the coefficients of the Taylor series of such an object are basically the moments. So it's kind of like a similar thing to like Taylor series having the derivatives as the coefficients of the Taylor series. Here, now we're dealing with like random stuff, so the moments show up as the in the coefficients in some way. Right. So, but all we really need is like the first couple moments for this next argument I'll be talking about. So let's just expand this a little bit. So this is like 1 plus, as a Taylor series, expected value of x. And let's just assume that all the moments actually exist. So yeah, this function doesn't necessarily have to exist. That's one problem with it, but let's assume all the moments exist, and yeah. Okay, so 1 plus the expected value of x times t plus the expected value of x squared over 2, t squared. And then there's going to be some higher remainder terms. Okay, and the remainder terms have all of the like higher powers of, all the higher moments, meaning expected value of x, expected value of x squared, then there'd be expected value of x cubed term. Yeah, the kth moment of a random variable is the expected value of x to the k. Yeah, exactly. So all the higher terms will, they'll have these like higher moments in them. But for this next argument, for the central limit theorem argument, basically we just need to know these first two. And we also need to know that this remainder term has like t to the third and higher powers in it. So it has the property that if I take the limit of r of t over t squared, see if I maybe get a better marker. That one might be better. Let me try to rewrite that. Okay, so if we take the limit, this thing has all t cubes in it or higher, so the limit of r of t over t squared as t goes to 0 is actually just 0. So this is important. Are there any questions? Can you see the board, everyone? Is this big enough to see? Right, so moment generating function, it's basically this power series, and the coefficients contain the moments if they exist for the random variable, which if it's a random variable on a finite probability space, then all of the moments will always exist, and everything's fine here. But yeah, and then this remainder term has the property that if we divide it by t squared and we let t go to 0, because it has all these t cubed or higher terms, the limit is still 0. Slim was a quant. Wait, did I miss a? Often people are interested in the centralized nth moment, in which case you want. Yeah, right. Right, yeah. Sorry, I missed your text. That's correct. Yeah, these are the regular moments, not the centralized moments. Yeah. Okay. So yeah, what is the central limit theorem? And also, let's just note that I don't want to go through the calculation, but the standard normal variable has a certain moment generating function, which we'll talk about in a second. Does anybody remember what it is or know what it is? So we have, this is like the PDF. For the standard normal variable, it has mean 0 here, and it has standard deviation like 1. And I think the PDF is like, 1 over square root pi, maybe there's a 2 down there somewhere. I forget the PDF, but I won't need it. I just basically need the moment generating function. Mean value variance. Yeah, so the moment generating function for a random variable that's a continuous random variable that's, can take any value that's distributed according to this normal distribution, the moment generating function is e to the t squared over 2. So this is just something this is something you could look up, or you can, try to calculate it yourself. But if we call this, maybe I'll call this like n for normal. And then, so n of the moment generating function for n of t is just e to the t squared over 2. And the t squared over 2 is in the exponent here. Okay, so that's our standard normal, and there's a theorem that basically says, so we're trying to prove the central limit theorem that says if I take this normalized sum of variables, in some limit I should be getting this normal distribution. So essentially, there's this Levy continuity theorem that says essentially I don't need to check like the PDFs at all. I can check, according, with some stipulations first. As long as the moment generating function of the things in the limit converge to this, then I'm good. So essentially the argument is just going to go, okay, we're going to look at the moment generating function for like each finite step in the central limit theorem, and then we're going to prove that the moment generating functions of the finite stuff converges to this pointwise. So for every t, we just get this function. And yeah, that's basically the argument. Does anybody have any questions about that? So it just says we can prove that the limits converge in distribution if and only if the moment generating functions converge to this. So essentially, that's what we're going to show. And yeah, just remember this property because I'll probably erase this, but I'll need this later. Or else one of the steps won't make sense. Okay. Right. Just before I go on, let me see if I can get one more good marker going. I don't know why I don't think these markers were very good. I got from Amazon. They go dry very fast, it seems. Or I'm just using them very quickly, which is also possible. All right, no questions. I don't see any. All right, has anyone seen moment generating functions before, or is this new to pretty much everyone? I'm sure Slim, you've probably, yeah, I mean, you've seen it probably. And there's also a related thing that I'm not really going to get into, but that's the characteristic function. And the characteristic function is like slightly better because it always exists for any random variable, even if the moments don't exist. But yeah, this argument can kind of be tweaked for the characteristic function. But yeah, I think it's a little bit simpler. This written out this way. And so, remember last time we had this finite binomial model and we were taking a limit. So the next step after we prove the central limit theorem is we want to apply the central limit theorem to that binomial model stuff and show that in the limit we get the Shreve result. The result in, I forget what page it was, but it was somewhere in the hundreds in the second resource, the continuous models Shreve book. Slim taught financial math on Twitch before. Okay, yeah. So yeah, I'm sure he's seen this stuff. But this isn't even really financial math. I mean, moment generating function is so broad it really applies to like any random variable, right? So, but yeah, I'm sure if he's talked about this central limit theorem, then you probably need to mention it. So yeah, what does the central limit theorem say? And then we'll prove it. Okay. There we go. That's a nice marker. Okay, so what does the central limit theorem say? At least there's a little bit like of you know, variation in how you can state this. So this is a little bit of a restricted version just to make it slightly easier to prove, but you can trust me that the more general proofs are not much different. So let's just say we have a bunch of random variables that are all identical, and we're going to add them together. So we have a bunch of x1, x2, xn. Let them be identically independent and identically distributed, meaning that they all have the same distribution and there's no like correlations between them or, you know, any dependence, right? Right, we had a definition of independence. I went over it like, you know, maybe 6 or so lectures ago, but yeah. The importance of the independence part is that you can show that if you add two independent variables, that it translates into the moment generating functions as multiplication. So that's the really important part about this. And the fact that they're identical just means that all the means and standard deviations and all the moment generating functions will be identical. So that's the other important part. So independence gives us the multiplication of the multiplication of the moment generating functions when you add the variables, and the identical part just means all the moment generating functions are the same. Okay, so we have a bunch of random variables. They're all the same. At least they come from the same distribution, and you know, we just pick n of them. We add them together. There's some numbers. Let's assume all the moment generating functions exist with the same moment generating function x of t. And let's also just assume that it converges in some open neighborhood, but really it converges everywhere because, well, actually, I don't know if that's true really. Maybe it's not. I think for a finite variable though, I think it always converges in a finite neighborhood. Maybe that's not true. So let me just assume it. Yeah, so let's just say we have a bunch of variables. They're all identically distributed. They're all independent, and they all have the same moment generating function, obviously, if they're all identical. And let's assume it converges in some open neighborhood of 0. I don't even know if we need this, but so i.e. like some negative epsilon to positive epsilon. Yeah, at least for the finite stuff I'm gonna need it for later. I'm not sure if we even need this, but oh, Jeff's here. Okay. Behold my glory. I am unworthy of his honor. Yeah, Jeff, I got gifted or I have a gifted sub. I have to give it out to someone, so I don't know. Well, I don't know how we'll figure this out. Okay, so we pick a bunch of variables. They're all identical. We add them together, and we do a normalization. There's a normalization factor. Also, we're going to assume that the expected value of each one is 0, and the variance, which is actually, I could just write it as the second moment is the variance if the expected value is 0, and we're going to assume this is 1. So the mean is 0. The second moment, which is also the variance here, is 1 for each variable, and then we're going to define a new variable, which is this basically normalized sum, Zn. This is just the sum of the xi's, and then I divide by square root of n. Yeah, so then the statement of the central limit theorem is then this variable converges in distribution to the standard normal variable, which we write as like n01. So then Zn converges in distribution, which, like we said, it just means the moment generating functions converge pointwise to that normal distribution one. And it's just going to be normal distribution with mean 0 and standard deviation 1, and that's because of this normalization factor here. Otherwise, the variance will be growing. Okay, any questions about that? I think this is a good marker. I like this marker. So we have a bunch of variables. They're all the same variable essentially, but it's like we're picking from the same bag a bunch of times independently. You could think of it like that. And they all have the same moment generating function, which converges in some open neighborhood of 0, like negative epsilon to epsilon for some epsilon greater than 0. And we're assuming each variable has expected value 0, mean 0, and variance 1. So they're like, if they're not this, you can normalize them. Like if the mean is not 0, you can subtract off the mean. If the variance is not 1, you can divide by the standard deviation, right? Right. So it seems like it's specific, but it's really not. It's really just saying, these don't have to be 0 and 1. If they're not 0 and 1, we can always like adjust it to be 0 and 1. So, but yeah, if this is the case, then we can define this new variable, and this new variable, once we do this, add them all up and do this scaling, then this is basically getting closer and closer to being a normal distribution. In the limit, it's getting really much closer and closer, which means that which is if and only if the moment generating function is converging pointwise to the moment generating function of this, which again, just to remind you, is mn of t, which is e to the t squared over 2. So we're basically trying to show that the limit of these zn's, the moment generating functions of these, converge pointwise to e to the t squared over 2. So Gemini said you can click him name in the chat to bring up his card and click gift a sub. Oh yeah, I can probably just do it from here. That's true. Gift a sub. Huh. I don't think it recognizes it here. Wait. I might need to do it from the desktop or from the browser. Right. So yeah, this is what we're gonna prove. And like I said, the method of the proof is we're gonna write down the moment generating functions of this variable zn. It's going to depend on these mx's. It's basically just going to be some product of them because they're all independent, like we were talking about. And then you're just going to show that you have this giant product, and in the limit, you have to show that basically it converges to this pointwise, which just means you fix some t and then you show it converges to this. All right, if there's no questions, I'll just move on to the proof. So yeah, we're going to prove the central limit theorem first, and then I'll move on to using this to prove the Shreve statement. And I'm kind of moving away from the notation in Shreve. It's not my favorite. It's basically the same argument, but I'm going to write it differently. It's just personal preference, I think. But hopefully, if you watch this and then you read the book later, his proof will make maybe a little more sense if you watch this first. So it's essentially the same argument, but it's just reworded a little differently, I think. Okay, but let's prove this first. I was actually in another stream before I was lured here by loot. I must now return. Hope to catch you later. Okay, no problem. Okay, so that's the statement. Any questions about the statement? This will be the proof. And I guess you could say this is like slightly hand-wavy proof because I'm using something that we haven't proved like I said, which is if the variables are independent and we add them, then the moment generating functions multiply. So I'm not going to prove that, but I'm definitely going to use it. And that means that I can write down the moment generating function for this Zn. Remember, Zn was this sum, right? Zn was the sum of xi's, and then I divide by square root of n. So because this is just a sum of a bunch of xi's over square root of n, this is actually just the product of the moment generating function for each of the x's. And then since I'm plugging in xi over square root of n, you can show that also this is just t over square root of n. Actually, I guess I'm using two statements here. Let me be a little careful here. Yeah, so this is actually based on two different things here. This is based on, one is that the xi's are independent. And the independence means I can multiply them all. So that's why I have this to the power of n here. So that's the fact that I'm using 1 here. And then 2, I'm using the fact that if I scale each of the variables by dividing by square root of n, it scales the moment generating function. So I can just plug in t over square root of n here. Okay. So with these two facts, oops, wait, I meant to say this is equal to this, of t. Let me just rewrite this. So m zn of t is equal to, it's a sum of a bunch of these variables. Each one has this moment generating function. They're all independent. So I take it to the power of n. There's n of them. And also each one of these, since I'm scaling this, you can scale the moment generating function. So basically you just scale the t variable. Okay. And now we're just going to expand this, right? Because remember, we had a way of writing this down with a remainder term that had a certain property when we divided by t squared. So this is, it was 1 plus t squared over 2n. This is because the mean is 0, so the t term has a 0 in front of it, so there's no t term, and then the variance is 1, so we just get t squared over, actually, no, wait, hold on. Or, yeah, the variance is 1, but then we're plugging in t over square root of n. So we have a 1/2 term from the Taylor series, and then we're just plugging in t over square root of n, but it gets squared, so we get t squared over n, yeah. So here, this comes from the fact that this is the expected value of x is 0, and the expected value of x squared is 1. Or that's why we can say this about that. Right, and then what is left? So we have this remainder term, right? Of t over square root of n. To the n. Okay, so basically, yeah, we're just rewriting the moment generating function as the way I wrote it before, using the mean and the variance, or the mean and the second moment, and then we have this higher remainder term. And now I'm going to do a little bit of rearrangement. So we're trying to prove that this is like e to some power. And if you remember your limit for e, remember you have this limit that's like, you take 1 to x over n, and you take it to the power of n. And as the limit as n goes to infinity, this converges to e to the x, right? Does everyone remember this? Right? So we're trying to remember in the end, we're trying to show that this thing is converging to e to the t squared over 2, right? So we're basically trying to show that in the limit as n goes to infinity, this is approaching e to something, right? We want it to be e to the t squared over 2, right? So essentially we want like this part, we want to put it up here somehow and then show that this part kind of goes to 0. And we just end up with this t squared over 2 n to the n power. And that limit, that goes to what we want essentially. So what I'm going to do here is I'm going to rewrite this as 1 plus t squared plus 2n r of t over square root of n over 2n. So just, what's it called? Making, getting a common denominator, right? So just give it a common denominator by multiplying by 2n. Now we can add it on the top here over 2n. And I want to show that this 2n r of t over square root of n goes to 0, basically. And then we'll get what we want because we have a sequence where this top thing is going to t squared over 2, and then you have divided by n, and then to the power of n. So if this goes to 0, then we're golden. Okay, because then in the limit it'll go to e to the t squared over 2. And that's what we want to show, according to this, right? According to this limit. All right, so any questions, guys? It's a pretty cool argument, though. I mean, like, you're taking a bunch of moment generating functions. It's one of these cool arguments where you have this, like, power to the n, and you got to use this property of e to the power, right? There's a lot of, like, identities for e to the power of x, right? This is just one of them, but we also have, like, the Taylor series is another one. But yeah, here we're using this. All right, no questions? Okay. So yeah, does anyone have any questions about that? Essentially, my argument is that if 2n r of t over square root of n, if this goes to 0 as n goes to infinity, then we're done. Does anyone want to argue with that, or does anyone not understand that? But if this goes to 0, then we're good, because then that means this whole thing is converging to just t squared over 2n to the n, and that whole thing is just converging to e to the t squared over 2, which is the moment generating function for the standard normal, which is what we're trying to show that this is converging to. Okay, and if this goes to 0, then we're done. So why is this the case? Well, it's basically just a change of variable. You have to change variable from like t over square root of n needs to basically convert into n. And then you'll end up with like some term on the outside, and the original property, remember I said that the limit of r of t over t squared as t goes to 0, this was 0. So you just basically need to do a change of variable, and then you use this property here. And then you can show this goes to 0. So yeah, I don't know if anyone wants me to write it out, but I don't think it's that complicated. I actually didn't write it out, but I just looked at it for a second. I think it's pretty easy. You just need to figure out what this change of variable is, and then once you do the change of variable to end up with an n in here, whatever you get on the outside, then you just use this limit. I think it's pretty straightforward. Okay, so if that's the case, if this does actually go to 0, then we say that then we can show that in the limit as n goes to infinity, this whole thing is converging to e to the t squared over 2. Point-wise, at least like if we fix a t, like there's not uniform convergence here, but we actually don't need it for the theorem. So we just need to fix a t. Just pick any t you want. It's a constant, and then if t is constant, then you can show as n goes to infinity with this property. This term here dies in the limit, and you just get 1 plus t squared over 2n to the n, and as n goes to infinity, this gets closer and closer to e to the t squared over 2. In fact, the limit is e to the t squared over 2 for any t. Okay, so that's basically, we're done. Because this is the moment generating function for the standard normal, and we showed that for any t it converges to that, and that's, yeah. Then by Levy continuity, which just says that if it converges pointwise to some moment generating function, then if you look at the limit of the distributions, then it converges in distribution to whatever the distribution that's corresponding to this one is. And there's also, I was looking up some cool stuff about, I was talking to Rex about this, but like, there's some weird stuff that can happen if the moment generating function exists and all the moments exist, but it's possible that it doesn't actually, the Taylor series doesn't actually converge for any t except for 0. And then you get into this like non-uniqueness thing, but here we don't have that problem because e to the t squared over 2 is analytic, and so it converges for all t. So you don't have that issue, and that gets rid of like some of the non-uniqueness. Yeah, if this didn't converge in any neighborhood of 0, it's possible that, I think it's possible that this theorem wouldn't hold in that case. Then we would probably have to use like the characteristic function or something like that, but yeah, let's just not worry about that right now. Yeah. Okay, so we take a limit of the m of the zn's of t, and because in the limit for any t it converges pointwise to e to the t squared over 2, then that means that these distributions, the zn's, are converging in distribution to the normal distribution. So we could write that as zn is converging in distribution to this standard normal. Okay, is that too messy, or is that, I think that was pretty good. Yeah, so that's basically the whole central limit theorem proof. At least in this simple case where they're just some random variable, they have a moment generating function, and the mean is 0, and the variance is 1 for each one. All right, so then the question becomes, how do we apply this to the picture we had before, where we had this binomial model where we had a stock that was multiplicatively going up or down at each interval, at each like period or step. And last time we wrote down that this limit was like approaching this, e to the power of, and then we had something to do with the normal distribution in it. So yeah, here I'm going to basically present the proof. It's essentially the same proof as Shreve, but in Shreve they waste a bunch of time, I feel like, talking about these scaled random walks, and I don't feel like it's very necessary because the whole argument basically just relies on this central limit theorem, and you don't really need to refer to it, I feel like. I am probably oversimplifying like one of the steps, but I don't think it's wrong. It's just maybe I'm not explaining enough. But I think it gives you like a very good intuitive picture of what's going on. So I think it's probably better than just being super pedantic and formal and like proving every little detail. But let me remind you of the setup from last time. So we have this sort of random stock, which is a price S0 at time 0, and it's randomly either going up or down by some multiplicative factor, which we call the U or D. Okay, so the statement in Shreve, Maybe Mavort, if you're still listening, you can get me the page number, but I don't have it off the top of my head. Actually, maybe I do. Yeah, actually I do. This is Theorem 3.2.2 on page 92. 92, and this is the second Shreve book. So this is Shreve Continuous Models. Or Continuous Time Models, I think it's called. There's like a stochastic calculus for finance 2, and then it's continuous time models is the whole thing. Okay, this is page 92, 3.2.2, and the full statement is that, you know, for the limit of this binomial model, we had it last time, right? It's like S of t is the stock price at 0 times E, and then in the exponent you have sigma, some Brownian motion at time t, which is just standard normal random variable with mean 0 and variance t. Yeah, then plus, or actually minus 1/2 sigma squared t. Right. Or, yeah, right. Right, so in the finite model, right, let's just forget about the t for a second, and let me just do it for like one period. T will basically be like how many periods we've gone, and you can like tweak the same argument for this arbitrary t. But let me just assume that basically we're going from t equals 0 to 1 basically. So yeah, for this finite model, basically we're breaking our interval from 0 to 1 up into pieces, and each piece is going to be 1 over square root of n size. So yeah, basically just break it into a bunch of pieces. And so the stock price at time at the end of the period, which I'll just write like as Sn of 1, this is going to be the stock price at time 0. And then I'm going to be multiplying by all these factors. So it's going to be a product from I equals 1 to n of these ri's, and the ri's will be distributed. Remember, these are our multiplicative factors, and ri is either 1 plus sigma over square root of n, you know, with probability p equals 1/2, or it's 1 minus sigma over square root of n. Again, with probability 1/2. Right, so this is just saying, you know, I flip a coin. If it's heads, I multiply by the up factor, 1 plus sigma over square root of n. If I flip the coin and it's tails, then I multiply by this 1 minus sigma over square root of n. All right, and that's basically how the stock price goes from 0 to 1 here. And this is our random model here. So the only difference with the central limit theorem here is that I can't use it yet because this random variable is a product of these random variables. So somehow I need to convert it to a sum, and then I can use central limit theorem, because the central limit theorem is about the sum of a bunch of random variables. And also note that all of these ri's are the same, right? They're all distributed the same way with this 50-50 chance. Okay, so does anybody have any questions about that? Essentially, we have the stock at time 1. It's determined by the price at time 0 and a multiplication by a bunch of these random factors. So to get to the end, I need to flip a lot of coins in general. And as n as n gets bigger and bigger, I need to flip more and more coins. Right? So there's more and more possibilities, is what I'm saying, that, you know, the stock price, I could flip a lot of heads and the stock price goes up really quickly, or I could flip a lot of tails and the stock price could go down really quickly, or, you know, everything in between, right? Any questions, guys? Okay, and then the t part is just essentially going to say that if I go to time t, I can kind of, as n goes to infinity, I can just keep doing this. I can just multiply by more and more things until I end up at time t. So for instance, like if t was 1.5, I could just keep letting n get larger and larger until, you know, I can actually multiply by enough of these, and then once I've multiplied by enough, I've, you know, 150% of the original interval would give me, you know, t equals 1.5. So yeah, I mean, maybe you need to play around with it in your head. It's a little bit confusing, but extending the finite model to any t, not just from 0 to 1, is not that hard. Okay, so essentially, like I said, we want to use the central limit theorem. We have a product here. I need to get a sum to use the central limit theorem. And it makes sense, right? Because we're trying to show that this is like e to the power of something. So taking a log and then showing that the log has something to do with the normal distribution. That makes sense, right? The log is going to have a sum of a bunch of variables, and that's going to have a central limit theorem involved, right? So what we're going to have to do is we need to take a log. Yeah, and we need to look at the random variables that are the log of the division of these two, right? Because that's going to be the sum of the ri's, or the sum of the log of the ri's. So what we want to be looking at is that the log of this Sn of 1 over Sn of 0, this is a sum of logs, of the log of the ri's. Okay, and then we want to use central limit theorem on this sum, because all the ri's are identically distributed. They all have this same distribution. Yeah. So then the question is, remember the Jensen's inequality is important because once we take the log of these variables, remember the original, the mean of these, the ri's is 0, right? But once I take the log of the ri's, the mean actually gets lowered. So that's important. And that actually shows up in this. That's where we get this, you can think of this as like the Jensen inequality term. It gives you negative drag because of the log property. The expected value of the log is lower than the log of the expected values. Malvert says we have a product, but we need a sum. My first thought was logarithm. Yeah, of course. A lot of these problems are solved this way, right? I think complex analysis, there's a whole story about Weierstrass factorizations, and it's like basically like kind of like a Taylor series, but it's like an infinite product instead, and then you can just take a log and an infinite product becomes an infinite sum. So yeah, whenever you see a big product of something, just think, wouldn't it be nice if that was a sum? And then just take logs. So seems to work 99% of the time. So yeah, we have this giant product, right? As n is getting bigger, there's more and more factors here, but no matter how many factors are here, we can just take the log of this divided by this, and it's just this sum right here, sum of the logs. Okay, so that's basically the statement. And what we want to do is we want to use the central limit theorem on this sum to say that this is approaching some normal distribution. But like we were saying, it's just one caveat, because it's we're taking the log of these variables. There's going to be some Jensen correction term, which is going to kind of bring the mean down, because the mean starts out at 0, but once we take logs, it changes. Okay, I think that's good. Right, and we're also going to need the Taylor series of log. So this is very important. The Taylor series of log, actually, the second derivative gives us an estimate on how much this expected value is being pulled down by transforming this variable by log. So not only does Jensen's inequality tell us that when I change variables from Ri to log of Ri, that not only does Jensen's tell us that the mean should be pulled down with this log transformation, but it gives us an estimate on how much it will be pulled down, because the second derivative in the Taylor series of log, basically, yeah, I mean, the Taylor series of log gives you the exact amount, but the second derivative is like your second correction term, and if it's negative, then it's saying that, you know, we're correcting by bringing it down. So yeah, so let's write down what is the Taylor series of log, just to remind ourselves, because we're going to need the fact that this is 1 plus sigma over square root of n, and we're going to be taking a log of it. We're going to need the Taylor series of that. So let's write that down. Oops, I erased the page. I think it was like 92. Right, so let's write down the Taylor series of log. This is the natural log, base e, in case you weren't sure. Right, so this is x minus x squared over 2, and then it just like alternates like that. Okay, do I really need to, I need to get rid of this. It's log base e, but yeah, I'm not writing the e. Okay, then, so what is the expected value of each of the ri's then? Or sorry, each of the log of ri's? I guess I could just do it like that. Right, that's what the xi's were, right? Yeah, xi is log of ri. Right, yeah. So you can just think of what's expected value of xi, where xi is log of ri, where we, you know, basically change variable here. Right. So by definition, there's only two outcomes for ri. So it's actually easy to write this by definition. This is just the 1/2 of the log of, you know, what can ri be? It can be, I can plug in for x either sigma over square root of n or negative sigma over square root of n. So it's either, yeah, sigma over square root of n minus sigma squared over n over 2n plus a bunch of other stuff. Or it could, there's also a 1/2 chance that it could be negative sigma over square root of n minus sigma squared over 2n plus a bunch of other stuff. Right. And so basically, these terms cancel. The sigma over square root of n and the negative sigma over square root of n cancel. And we just end up with two of these negative terms. So it's negative sigma squared over 2n times 1/2, but then we're doing two of them, so it's just negative sigma squared over 2n. And you can show that all the other terms are actually big O of n to the negative 3/2. And that just means that there's like a lot of n's at the bottom, basically. There's at least, you can factor out an n to the 3/2 from them, essentially. Right. So any questions about this? So the whole point of this is to show that in the limit, as n goes to infinity, this is behaving more and more like negative sigma squared over 2n. This term begins to not matter more and more as n goes to infinity. And also for the variance, we have something very similar. So the variance, remember we proved a property that this is the expected value of xi squared minus the expected value of xi squared. Right, and we already have the expected value of xi right here, so we can just square that. And then the expected value of xi squared is a little bit different. So that's, now I need to plug it into log. Yeah, so this you can show is approximately sigma squared over 2. And then again, you have this O n to the negative 3 halves. Okay, so the whole point of that is to show that in the limit as n goes to infinity, the expected value of these xi variables is behaving like negative sigma squared over 2n plus some term that's going to 0 really quickly. And then the variance is approximately sigma squared over 2 plus, again, something that's going to 0 really quickly. Oh, sorry, this is over n, not over 2. Yeah, so basically we have some term over n and then plus some term that's going to infinity faster than n. Same thing over here, negative sigma squared over 2n plus some term that's going to 0 really quickly as n goes to infinity. Okay, and the whole point of this is to show that we're going to use some sort of central limit theorem argument here to say that, well, our variable before was just a sum of n of these, right? So the expected value is just this times n. And because we multiply by n, this thing's still going to 0. So that's the important part. And then when we multiply by n here, this thing is sigma squared, and this part's still going to 0. So yeah, I'll write it out in a second, but that's essentially the argument. This is the expected value and the variance for each xi variable. Our new variable is, we're going to use the central limit theorem, so we're going to add all of these together. Once we add all of them together, we just need to multiply this by n and this by n to get the expected value of the sum and the variance of the sum. And then when we multiply by n, this part still goes to 0, so it doesn't matter. And then so in the limit, the variance is approaching sigma squared for the sum, because we're summing up n of these. And then in the limit, when we sum up n of these, we get a mean of negative sigma squared over 2. And that's how you ended up with that Jensen term, the negative sigma squared over 2 term in the answer. Okay, so basically this term is just a Jensen correction term based on the fact that this second term is negative here for both of these. And it has the same sign. So that's important. Whereas these cancel out, right? They have different sign, but the degree 2 terms actually don't cancel out. Okay, and they add up to this. Okay. No one has any questions about this? So this is the first part of the argument, and then we just need to make some sort of argument about when we add up all these xi's, what happens. So that's going to use the central limit theorem. Let me get a water real quick. Oh, I got one right here. Can you explain the third line again? Oh, I just erased it. What was the third line? Are you asking the O of n to the negative 3 halves part for both of them? What was it? Yeah. Negative sigma squared over 2n plus that, and the variance was sigma squared over n plus O of n, negative 3 halves. I mean the part with the 1/2. Oh. Yeah, so there's only two options. There's only two values that the xi can take on, right? It's either going to be log of 1 plus sigma over square root of n, or with a 1/2 chance, right? So 1/2 chance it's going to be this, or a 1/2 chance that it'll be this. So the mean of the variable is just 1/2 of this plus 1/2 of this, and then you use the Taylor series. So for the Taylor series, it's going to be 1/2 times this plus 1/2 times this. If I expand the Taylor series, it's like 1/2. Yeah, what I had before. So you just have, it's 1/2 sigma over square root of n minus sigma squared over 2n plus a bunch of lower terms. So notice that the factor of n is getting larger, right? It's n to the 1/2 on the bottom, then n, then the next term will be n to the 3/2, then n to the second, then n to the 5/2, and etc. So that's for the first part, plus 1/2 of the second thing. So now I just need to plug in negative sigma over square root of n into the Taylor series. So it's negative sigma over square root of n. And then here's the trick part. So the second part is still negative because it's minus, and then when I square it, it's still positive. So sigma squared over 2n again, plus a bunch of lower terms. So 1/2 of this plus 1/2 of this, the first terms cancel. 1/2 of this minus 1/2 of itself is 0, and then these terms add up. So, yeah. And then everything else is O of n to the negative 3/2. Okay, cool. We're good? Yeah, and the variance calculation is similar. You just need to do a little bit more manipulation with the Taylor series. Okay, so then what we want to show is, remember the S0 variable was, or sorry, the S of 1 variable was, I started at S of 0 and I'm multiplying by a bunch of these xi's. But then we took a log, so the log so essentially we have, we want to show that the limit as n goes to infinity of Sn of 1 over Sn of 0 is basically normally distributed, and, or sorry, the log of it. So log of this is normally distributed. Yeah, or converges in distribution to the normal distribution with mean negative sigma squared over 2 and variance sigma squared. So basically a shifted version of the standard normal. Instead of it being standard normal, the mean got shifted by negative sigma squared over 2, and the variance is still just sigma squared. Okay, so how do we do this? Again, we're going to use central limit theorem. So we just said that the log of Sn of 1 over Sn of 0, this is a product, this is a sum of a bunch of variables, right? This is the sum of the log of the ri's, or another notation was we just said it's the sum of the xi's. Right, and then we know, we just wrote down what the approximate mean and variance was for each xi. So then when we add up these identically distributed and independent variables, we should have a central limit theorem. So central limit theorem says that the sum of the xi's converges in distribution to, so here you have to do a little bit of scaling. Like you'd have to rescale all of the xi's so that their mean was 0 and their variance was all 1. But if you do that, then you use the central limit theorem and then you rescale everything back. So essentially you're just showing that the You need to like do a little bit of thinking about this, but the central limit theorem does say that the sum of the xi's is converging in distribution to this normal distribution. Or actually, I don't know why I want to show here. Basically, we did show this by proving the central limit theorem. So the central limit theorem says this because of what we just wrote down. Yeah, because basically, yeah, because the variance was getting closer and closer. Here, I erased what I had before, but maybe it's important to have it. So the expected value of each xi was approximately negative sigma squared over 2n. And then a bunch of terms that didn't matter, right? So the expected value of, or the variance of the xi's was also approximately, not exactly equal to, but approximately sigma squared over n. And so that just means if we're adding up n of them, right, this is I from 1 to n, then because they're all identical, all the means are going to add. So we just have n of these, so if I add up n of these, it just gets multiplied by n. Then I just get negative sigma squared over 2 for the mean. And if I'm adding up n of these for the variance, well, the variance is also just add when I have independent, random variables. So if each one is sigma squared over n, and I'm adding up n of them, it just gets multiplied by n, so I just get sigma squared for the variance. Okay, and then we proved the central limit theorem. So each one of these is identically distributed and independent. So central limit theorem says I should be getting this in the limit. Actually, technically we just proved if I rescale everything and shift everything, then it converges to n of 0, 1. But you can also show that if you just unshift and multiply back, that it's obviously just going to converge to a different moment generating function. It's going to be the moment generating function of this normal distribution. Okay, so this is like very slight hand wavy, but you can be confident in me that this is very slight hand wave. Essentially, you just have to rescale and shift these, and we proved it converges to n of 0, 1 for the shifted stuff, and then you just unshift. So a little bit hand wavy. I'm waving my hands here a lot, but it's really not that bad. Okay, and then we're essentially done because we showed that the log of this ratio, which is this sum, is getting closer and closer to normal. And so that means that if I change variables back by, taking e to the power of both sides, then I'll get that Sn of 1 over Sn of 0 is e to some variable that's normally distributed, right? So that's our conclusion essentially here, that because this is converging in distribution to this, if I switch back from the log back to e to the variable, so Sn of 1 over Sn of 0 is e to some random normal variable. And another way to write this, we can use that W notation from last time. So we can say it's just e to the power of sigma W of 1 minus sigma squared over 2. Because that's the mean. And this is just a random normal variable with variance 1. And when I multiply by sigma, it's basically just standard normal with variance sigma squared, and then I subtract by sigma squared over 2. That gives me that shifted mean. So that's what I was talking about when you can just rescale and shift, and yeah, so that's basically the rescaling and the shifting. And yeah, then we're basically done because this is essentially the same statement. You just need to basically tweak the argument and replace 1 with t, and you'll end up with a t here. So it's essentially the same argument, but you can show that also Sn of t can be then written as Sn of 0, and then e to the sigma W of, and then instead of 1, you can replace 1 with t. It's essentially all the same argument. You're just going to replace this 1 with a t. And then you'll also end up with this sigma squared over 2 times t term as well. But t is 1 up here, so just multiplied by 1. Okay, so slight hand waviness here using the central limit theorem, and slight hand waviness at the end. You just got to trust me that the argument is essentially the same here. You just end up with, when it's an arbitrary t, you just end up with w of t here instead of w of 1, and you end up with an extra t factor at the bottom here. But other than that, it's essentially the same argument as what we just went over. And I just want to stress here that the real power, or the real crux of the argument, is depending on this Taylor series for log, and the fact that the second derivative is negative. That's why you end up with this negative drag term here once you change coordinates to the log space. Okay, so the variance brings down our mean here. In the multiplicative case, when we're multiplying by stuff, even though the things that we were multiplying by had mean 0, when we transform to the log space and we get a sum, it brings the mean down. So this is a Jensen inequality thing, and the variance is somehow unaffected, but we do get this drag on the mean here in general. Okay, so yeah, that's pretty much the whole argument. That's pretty fun. Central limit theorem, and then we use the central limit theorem to show that this multiplicative process that's being multiplied up or down, when we change to this log coordinate, it basically shifts the mean. But other than that, we get a nice relationship. And then in the log variable, it's standard normal. So the normal variable is like log normal, which means that it's like e to some normal random variable. And that variable has variance sigma squared. And the mean gets this Jensen shift term. Okay, and then that's basically what we want to show. This is like our geometric Brownian motion solution in some sense to the stochastic differential equation, which we haven't talked about. But this is sort of like an introduction to all that stuff. So like I was saying, you kind of want to think of this as a solution to some like random stochastic type of differential equation. It's analogous to, you have the standard one, which is like dy dx equals y, and then the solution is e to the x, right? This is some sort of like e to the x solution, but for a random version of that. Okay, so that was less complicated than expected, but still a little weird. I need to look at the central limit theorem again. Yeah, it's a little bit of hand waviness here, but really this is kind of standard hand waviness, I feel like. This isn't anything too crazy. I think my argument is a little bit it's essentially the same argument in Shreve if you really go through it carefully, but I feel like the way I present it here, it's a little bit simpler, but maybe I'm just biased. I don't know. The Shreve stuff seemed a little bit more convoluted because he went into random walks first, and then he went into scaled random walks, and he wanted to show that in the limit, the scaled random walks, you were getting this normal distribution. But it essentially was just central limit theorem. So I think I just maybe made the argument a little bit less convoluted, hopefully. Yeah, I think that's all we got here. So it's all really important. The crux of the argument was this Taylor series for the logarithm, for the natural logarithm. All right, I think I'll end it here. I'll look for someone to raid unless anybody has any questions. But yeah, that was pretty fun lesson. Only question Mavort has is, why was R defined as the product with sigma over square root of n? You mean why was the square root of n term in there? Why did we define each Ri as this? Why is this the term that we picked to multiply by? Is that the question? Right. We said the Ri term that we're multiplying by is either, it has 50% chance. I don't know how to write this. What's a good way to write this? 50% chance that it's going to be 1 plus sigma over square root of n. 50% chance that it'll be 1 minus sigma over square. So why are we picking this over square root of n? Or why is this the term in general that we're multiplying by? Is that the question? The only question, maybe you can explain the definition of R again. Right. So R is just this random variable. I guess you can think of this as, yeah, it's sort of funky. It's almost like you need this to be this way. Actually, yeah, you can tweak these. This doesn't have to be this way. You can tweak these probabilities in this, but it's going to change the mean here. So there is a more general version of this. I'm not sure if I'm answering your question, but these actually don't have to be the same, and these probabilities don't have to be the same, and then you just get a more general formula here. So I think he's trying to simplify it. He's trying to make it so that these are like symmetric. I think it just simplifies the argument, but you can still prove it even if they aren't the same. Yeah, so my only explanation is that it's to make the argument a little bit simpler, and that's because the mean of these is 0. In the more general term, you're going to end up with like a mu term here because the mean doesn't have to be 0. So I think that the more general one you're going to end up with is like something like mu minus sigma squared over 2, where mu is the mean of these. Here it's just 0. And then, yeah, this I think is still just sigma squared. So yeah, he just picks these so that the mean is 0. I think that's the reason. And then this term just drops out, and the proof gets a little bit simpler. Yes, I get why R is a product because we know they're independent, but why is there a sigma over square root of n? Yeah, I think I just explained that. So, I mean, you can replace these with other terms. It's just gonna change, the way this formula looks. So, yeah, you can change all this stuff. I mean, you could just change this to like 1 plus u and 1 minus d. But then you're just gonna have like a u and d in this formula instead of sigma. So it's just going to change the look of the formula, but the content is going to essentially be the same. Yeah. I think that explains everything. So yeah, there's a more general formula. You're just going to end up with like, either you rewrite these with different variable names, or you're going to end up with some sort of mu term here. Any other questions in the chat? Oh, yeah, I had a log here, right? Yeah. Is there a way to write a random variable? I don't know, this is my notation, but I feel like this is not the right way to write it. Yeah, that's what I meant. It was 1 plus u and 1 minus d before. That's why I was... Oh, okay, yeah. Okay, yeah, good. Yeah, so yeah, you can rewrite it. It's just going to change the look of this, but essentially it'll be the same thing. Okay, excellent. I think I'll end here. I don't see any other questions. I appreciate everyone who showed up, everyone who was interested in the talk. I can talk more about this stuff, but I think I might take a little bit of a break after this to do maybe some complex analysis, or I don't know, I have to think about it, maybe number theory or something, but I really like complex analysis, so. Yeah, unless anyone wants me to go more in depth with this, I can go into some sort of like more like option-y type math. Like we didn't really talk about options too much. And I could also get more into like replicating formula stuff for some sort of like weird type of derivatives, which are kind of interesting. But okay, Don is on. Wasn't he on earlier? Or maybe that was yesterday, right? I'm starting to, all the days are blending together. All right, let's raid Don. Hopefully there's still some people in here to raid him. Don Factorial. Great math streamer, some occasional video game streamer, and yeah, just a nice guy. So let's say hi to Don. And I'm going to send it over. So I hope everyone has a good day, and I hope you enjoyed that lecture. Central limit theorem, very fundamental theorem for probability theory, and also moment generating function. So yeah, we did a lot today. All right, everybody enjoy. Raid.